So today we're going to be looking at section 11.2, inference for two-way tables. Okay, we're looking at, basically, yesterday we looked at like a single categorical variable, and now we're going to kind of be looking at tests that involve more than one categorical variable, because we collect our data, we may have it organized into more than one categorical variable. Our objectives for this lesson, we're going to compare conditional distributions for data in a two-way table. We looked at conditional distributions before, way long ago. It's been a little while. We really got to dig back far into our background knowledge for that, but we did that before. But we're going to revisit that today. It's okay if you're having trouble revisiting that right now in your mind, so it's okay. We're going to revisit that today, and we're going to compare those. We're also going to state appropriate hypotheses and compute expected counts for a chi-squared test based on data in a two-way table. It's a little different when we're in a two-way table the way we did it for one, when we have just one categorical variable. It's a little more complicated now. We're also going to calculate the chi-squared statistic, degrees of freedom, and p-value for a chi-squared test based on data in a two-way table. And we're going to perform, there's two chi-squared tests we can perform here. We can perform a test for homogeneity, and we can perform one for independence. And then choose the appropriate chi-squared test, of course, depending on what the situation is. So introducing the two sample Z procedures of chapter 10 allows us to compare proportions of successes in two populations or two treatments. What if we want to compare more than two samples or groups? More generally, what if we want to compare the distributions of a single categorical variable across several populations or treatments? We need a new statistical test. And the new test starts by presenting the data in a two-way table. Two-way tables have more general uses, though, than comparing distributions of a single categorical variable. They can be used to describe relationships between any two categorical variables. So we could be looking at gender and some other categorical variable. Like, we'll look at examples here in just a minute anyways. Okay, so right here, market researchers suspect that background music may affect the mood and buying behavior of customers. One study in a Mediterranean restaurant compared three randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of customers who ordered French, Italian, or other entrees. So, is listening to that music or that particular kind of music going to make you want that particular kind of food? I don't know about you, but I hear like a mariachi band player or whatever, and I'm thinking, ooh, I want chips and salsa. But that's just me.
I don't know what French food is. Italian, yeah, I heard Italian music.
Italian?
A big old.
I want to play spaghetti,
Yeah.
meatball, yeah, something like that, yeah.
Pizza or something.
Yes.
But I don't really, yeah, chips and, I guess, yeah, chips and salsa. Or like
I don't know really what, I don't know, I don't know what French would be either. I know they eat escargot.
What is French food?
They eat escargot.
Is that snail or is that?
Yeah, that's snails.
I've ate snail before.
Pretty sure it's
It wasn't that bad, actually.
Calm down, Charlie D'Amelio.
Yep.
I think I'll have to pass.
Okay, French food is, you got.
French onion soup, French fries.
No.
The other two don't know.
Okay, look, French food, okay. Palmieri's pork relitos, lobster biscuit, tuna doesn't know, beef burgundy, lemon crepe, ratatouille, spinach,
Crepes.
I've had lobster.
Yeah, crepes.
before,
Yeah,
and it's really good.
French toast is French food, lemon meringue
Really?
pie.
I
Yeah,
wonder if it's the same though.
it looks the same. It
Because
looks
we
like
Americanize
it looks
a
like
lot
a
of
piece of
things,
toast.
just FYI.
It looks like a piece of toast with syrup and butter on it. So I assume it's.
Okay.
That's it. Ooh, also donuts are French cuisine. Cherry pie, most of your pies and cakes like muffins, cannolis, macaroons, carrot cake, brownies are French. Apple strudels, banana bread. Oh my gosh, yeah, I'm gonna start
I
thinking.
thought strudel was German. Could have sworn.
I think it's that type.
They're probably the different kinds. Anyways, moving on. So, they're looking to see about if they would, like under these conditions, if they what type of music they're listening to, what type of entree do they order. And looking to see, is there some sort of relationship between that? So what they've done is they've done the counts. How many people were listening to this type of music but ordered this kind of food? Okay, does that make sense as far as the two-way table? And where those numbers are coming from, that they just...
I guess American food would be ordering.
So 30 people were not listening, 30 people ordered French food, even though they were not listening to any music.
Mm-hmm.
And 30 people ordered Italian food,
Well,
or
ordered French while
French
listening-
food while listening to Italian music though.
Yes.
But 39 ordered French food when listening to French music. Okay.
Only one.
All right. So comparing distributions of a categorical variable to problem, calculate the conditional distribution and proportions of the entree ordered for each treatment. So we look at it. When no music was playing, the distribution of entree orders was, for French, 30 out of 84. Where are those numbers coming from? We go back to the table. 30 people that were not, the distribution, the conditional distribution here, for when no music was playing. So out of no music playing, 84 people were not listening to any music. You see where that number is? That's the total on that column right there. Okay, does everybody see that? 84 is the total on that was not listening to any type of music. 30 out of 84 is that conditional value right there, that of that one, which is 0.357. Italian was 11 out of 84, and other was 43 out of 84. So you've got those proportions there. That makes up our conditional distribution there. When the French accordion music was playing, the distribution of entree orders was, now these are out of 75 because if you go back to the table, 75 people were not listening to French music. Okay? And so there's those distributions. Only 1 out of 75 when listening to French music ordered Italian food. And then when Italian string music, there's the distribution there. More people ordered other things besides Italian food when listening to Italian music. Interesting. That's weird. All right, so making an appropriate graph for comparing the conditional distributions in part A. You've got your no music, French music, and Italian music, and the percents that ordered those particular entrees. So write a few sentences comparing the distributions. Well, the type of entree the customer buys seems to differ considerably across the 3 music treatments. Orders of Italian entrees are very low when French music is playing, but are higher when Italian music or no music is playing. French entrees seem popular in this restaurant as they are ordered frequently under all music conditions, but notably more often when French music is playing. And for all 3 music treatments here, the percent of other entrees ordered was pretty similar. If you go back and look at the graphs, all of the other ones are pretty similar. That's the last bar on each one of those graphs. They all look pretty much the same. These graphs are scaled all the same here, so it's really easy to compare them. Remember, it's always good if you're comparing different graphs to have them scaled the same. That way it's easy to compare. You got to pay attention to the scale so you're not distorting the data here and being deceptive. You got to pay attention to graphs in the media, because sometimes they will distort them, believe it or not. It's always good to really pay attention to that, okay? So then you got your, right here, and it seems that they're, like I said, French, it seems like a lot more people order French across all 3 treatments. All right, so the problem of how to do many comparisons at once with an overall measure of confidence is our conclusions is common in statistics. And all of our conclusions is common in statistics. This is the problem of multiple comparisons. Statistical methods for dealing with multiple comparisons usually have two parts. One, an overall test to see if there's good evidence of any differences among the parameters that we want to compare. And two, a detailed follow-up analysis to decide whether which of these parameters differ and to estimate how large the differences are. The overall test uses that familiar chi-squared statistic and distributions, what we're used to, okay? Hopefully we're paying attention, guys. Okay. So, chi-squared test for homogeneity begins with these hypotheses. One, the null. There is no difference in the distribution of a categorical variable for several populations or treatments. The alternative, there is a difference. Remember, the null is always a no difference kind of statement. It's true here as well in the sentence form. There's no difference in the distribution of that categorical variable. So in this case, there's no difference in what entree they order of a categorical variable based on what the music they're listening to. The music is the treatments. Okay, that would be the null in the case of the music example. There's no difference in what entree they order based on what music they're listening to, they're exposed to, or however you want to word that. Okay, it can be worded differently. You word it one way, I word it another way, someone else words it another way, we could all be right. As long as it's the same kind of general idea with that, yeah. So, and then there is a difference. So you're just changing a couple words. We compare the observed counts in a two-way table with the counts we would expect if the null were true. So that's where expected counts come into play. So consider the expected count of French entrees bought when no music was playing. Okay. 99 total French entrees were ordered out of the whole 243 people, but only 84 people were listening to no music here. So we're considering the expected count of French entrees bought when no music was playing. 99 total out of the total 243. Okay, and sometimes you have to calculate these, by the way. They don't always give these to you. So the very first thing you get a two-way table and it doesn't have the totals on a test or something, is for you to go through here and actually find these totals. Find the whole grand total, find the row totals, find the column totals. Okay, not in that order though. You want to find maybe the column totals and the row totals and the grand total. And make sure that, I'd almost want to make sure that these three add up to that, and also these three add up to that, so I didn't make a little math error somewhere along the way. I want to double check that. Okay. There was 99 total French entrees ordered. Okay, that's the number of French entrees ordered out of the grand total. We would expect there to be, if 84 people are not listening to music, we would expect that percentage, 99 out of 243, that percent of 84 would be the expected count to be ordered. Does that make sense? It's a little tough to understand that. Okay? You sometimes have to kind of think your way through it and even talk your way through it a little bit. 99 total out of the grand total. That's the percent of French entrees ordered. We would expect then, if 84 people are not listening to music, we would expect, if there's no difference, there's no effect here, we would expect that percent of 84 to order French entrees while not listening to any music.
You'd expect 30.
So in that case, it would be 34.22.
So what about since it's lower, what does that mean? Like it's 30 on the thing? but
So
it's
there's a
34.
difference.
Okay.
That starts to give us evidence. If we start having lots of deviations from the actual observed values, then we're starting to get evidence for the alternative. we're starting to get convincing evidence for the alternative. But the question is, do we have enough convincing evidence for the alternative? That's where the statistic will come into play. Okay, so the values in this calculation are the row total for the French wine in this case, I guess. What says wine? The column total for no music and the table total. We can rewrite the original calculation as this. 99 times 84 over the grand total. It's row total times column total over grand total. Row total times column total over grand total. Okay? So, when the null is true, the expected count in any cell of a two-way table is the expected count is equal to the row total times the column total over the table total or grand total. Okay? We do that for every single cell in the table. That will take some time to do. Right? So you hope for not a big table, obviously. And on a test question, you probably won't have no bigger than I'd say that one that we have right here in this example. Maybe a little bigger, but not much. Because you're not going to have to, do it for like 10 rows and 10 columns. That's ridiculous. All right. So you've got, but you could. You could. You got to check your conditions though before performing this chi-squared test. You got to make sure that the data comes from a random sample or randomized experiment. You got to make sure that when sampling without replacement, you got to check the 10% condition. Your sample size needs to be less than 1/10 of your population size, and all expected counts have to be greater than 5. That one stays the same. All these are the same conditions from the last section. Okay. But you'll have to find that expected count for each thing, and that's what they're going to do here. And just as we do with the chi-square goodness of fit test, we compare the observed counts with the expected counts using this statistic. Chi-squared is equal to the observed minus the expected squared all over the expected. We're just applying that statistic to a different kind of test, but it's the same. We calculate it the same way. Here's all the expected counts. So like they got this number right here, 30.56. They got it by taking 75 times 99 all over 243. Check that real quick. See if for this element right here, row total's 99, column total's 75, multiply 99 times 75, and divide it by the table total of 243. Did you get 30.56?
Divided by, what do we divide?
Divided by the table
Okay.
total,
I got 30.5555556.
which would round up to 30.56. Did you get that, John?
Yep.
The same thing? Okay. And so then, just to check another one, just to make sure, I want you to really see this. Let's do the middle one right here. This one right here, its row total's 31. So do 31 times the column total, 75, all over 243, and see if you get 9.57.
I got 5,000, wait, no.
75 times 31, all over 243.
I got 9.57.
There you go.
Okay,
That's what you should have.
observed, okay, so we gotta make it, okay.
75 times 31, all over 243.
How do we put it in the calculator? 'Cause now it's saying I'm wrong.
75 times 31,
75 times 31.
all to over 243, or divide it by 243 after you get an answer. I would do it as a stacked fraction, like I'd even almost start a stacked fraction,
So
and I would type it in as
Okay.
it's row total and column total?
row total times column total
Mm-hmm.
divided by table total.
See, when I did that, okay, so 70, what is it?
75,
75 times 31
yes,
over
243.
243, and I get 775 over 81.
Did you, but, I
So
know
like-
what you,
I would have to change that, correct?
yes, do alpha like what was number fractions of a decimal.
Okay.
Or math 2.
Okay.
Math 1 is to a fraction, but math 2 is back to a decimal. Okay, was that 9.57? I didn't even really
I
look.
got, yeah, 9.57.
So that's what they got right here in the expected count in that element. You can pick any one of these elements, like we could do this one. Well, to get this one's expected count, 84 times 113 all over 243, and that would come out to be 39.06. Okay? You have to do that for every single element. That's 9 expected counts that you'll have to use that formula for to do that.
So what is it we're finding exactly, like on that right?
The expected counts.
The expected counts.
Uh-huh.
Okay.
This is how much we would expect there to be if there really is no difference. If those treatments really don't have any effect, really. This is what we would expect there to be. Deviations from this to this is what gives us evidence of the alternative. But to calculate those deviations, that's where that comes into play. Now that we have all these observed and expecteds, we're ready to do that, the chi-squared. Now, who wants to go in there and do that now for all 9 things, after doing this for all 9 things? It's a lot of labor, isn't it?
Yeah.
Labor intensive. That's where the calculator will come in to help us. Okay. All right. So we get that. Now we calculate our chi-squared statistic, which would take forever to do by hand. But what you would do, just to show what you would do if you were to do it all by hand, I'll show you another way you can do this. But you would do the French entrees with no music. The observed count was 30. The expected count was 34.22. So you subtract those, observed minus expected, squared, divided by expected.
Okay.
And then that'll give you that. That'll be your first value. Just add up with all your other chi-squared values, all your other values to make up chi-squared.
Okay, so it's 30 minus?
34.22 in parentheses squared all over 34.22. And that should come out to be 0.52.
Yeah, 0.52.
Okay?
So what's 0.52?
That's part of the chi-squared statistic, but we got to do that for every single element, all 9 elements. And we're going to get 9 numbers to add up together. Okay? So the chi-squared statistic will be the sum of all those 9 terms, which comes out to be 18.28 when you do that. Okay, now I'll show you how we can get that an easier way here in just a moment. Let's see. Where's this going? Okay, yeah, let's do that. Let's do that right now. All right, so I'm going to show you how we can do this a little bit easier. All right, keep your paper on this slide right here. Okay, we need those 2 right there. We need these 2 things right here. We need to be able to see these 2 tables right here for what we're about to do on the calculator. What's another way in algebra or in math, algebra? What's another way in algebra to organize data into rows and columns? Do you remember something else from algebra where you organized numbers in rows and columns?
I'm not using a graph.
I don't remember none of that.
I do. I just don't remember exactly how to do it. I know exactly.
Do you remember what it was called?
It's like the input-output thing, right?
No.
I remember like a thick.
Isn't it like a graph and then you put dots on every number?
Okay, now some of you, to be fair, if you had Algebra 2
During COVID?
during the COVID semester, second
Me.
semester, anyone else had that? Okay.
I'm
Any-
thorough.
Okay,
It's been a fun year.
yeah, I know. To be fair, you didn't get to do these,
Oh,
okay? They're not hard, but they're something that you didn't get to do. Now, if you had Algebra 2 the first semester of last year, or you had it previous before that, you did this then. Another way you can organize data on the calculator into rows and columns is with something called a matrix. Does that sound familiar now? A matrix.
Yes. Yeah.
Okay.
Wait a minute. I'm moving on like the matrix.
All right. So I'm going to show you how to do that. Now, there are two ways to put a matrix in the calculator. And we have to use the way that you may not have learned, honestly, because unfortunately this test requires us to use it that way. We have to put these matrices. We're going to take this data right here. And it's like we're going to take this and put this in as one matrix of our observed values: 30, 39, 30, 11, 1, 19, 43, 35, 35. And we're going to put the expected counts in another matrix. And we're going to let the calculator do the work for us in doing all this. Because I don't know about you, but do you want to really do all this by hand? It'll take you a while. 9 different numbers you have to find up and add up. Okay, so we put this in as one matrix, this is in another matrix. Okay? You might want to make note of that. I'm going to erase this now so I can put the calculator on the screen.
Can you show us how to do
Oh,
that?
yeah, I'm going to show you how to do it. But I want to pull up the calculator on the screen.
Okay, so what do we need to write down? Matrix, put these in the matrix.
We're going to put these in the matrix. You might just want to make notes on how to do that, what I do on the calculator
Okay.
here in just a minute to the side.
Okay.
Okay, all right. I'm going to erase the bars now so that I can pull up the calculator on the screen here. Again, keep this paper handy because we need to have these numbers, because once I put the calculator up here, we're not going to have those numbers readily available.
You know what's a good lobster? Lobster. Is Outback a lobster? I think they do. I think they have shrimp on more of it. Straight Outback for prom. I think it's $25 gift card.
Oh, dude, wait, I have a good card too.
Outback?
Yeah, I think so. So I'm probably gonna
All
use
right.
my other one that I have.
This part you
Shadow.
probably want to follow along with me on your calculator, please, doing this so you can see this, okay? All right, are we all ready? Make sure you have your calculator ready. If you're at home, pause the video right now and get your calculator and then start it back up. All right, so to do this, you're going to enter and make the matrix in the calculator. We're going to hit second matrix. It's the right here above x to the -1 button. Okay, matrix menu. In this screen here, we have the names of our matrices. We have a math tab. If you recall from Algebra 2, this is where you can find the determinant of a matrix. It's where you can do some other stuff with a matrix. Of course, if you were COVID semester, you may not remember that because you didn't do that. There's ways to solve a system of equations with the matrix really quickly. It's really nice and neat, cool. If you want to know how to do all that, I'll show it to you later. But anyways, that's where you can do all that. But we're not going to do that. We're going to go over to Edit. We're going to go all the way over to the Edit tab, and we're going to put the observed matrix in for A. So on this tab right here allows us to edit them. So we're going to go to A, and it asks for the dimensions first. The dimensions are the rows, the number of rows by the number of columns. So looking at our observed counts, we have rows are horizontal, columns are vertical, like the columns on a porch. Okay, how many rows do we have on this right here? Don't look at the totals, but just those 3. We have 3 rows. So we need 3 rows. We hit the right arrow key to go over, and we need how many columns?
3.
3 columns.
Okay.
So we edit that so that it has that, and we hit the right arrow key out of that, and now we're down here And we should look and see that we have 3 rows, 3 columns.
Check.
And now we're just gonna go through and enter those numbers in the way that they were. The first number was 30, and I'm getting these from the table, from our notes.
Which table? Oh, man, wait a
I'm
minute.
doing the observed.
30.
The observed first, then the expected.
Wait a minute. Okay.
We're doing the observed, 30, 39. You just type a number in and hit enter, by the way, guys, and it'll take you to the next element. It'll go through all the rows, 1 row at a time. The next one is 30. Then it goes down to the next row. Okay, because we're done with row 1. Row 2. Just like they'll call you all up on graduation. Row 2, please stand now.
Hey, why
Okay.
you gotta hurt us like this?
Sorry. I'm just saying that's what that would come to mind there. All right, row 2, 11, 1, 19. Okay. Row 3, 43, 35, 35. Has everybody got their observed in?
Sure.
All these numbers now. You're seeing where I'm getting these from. I'm getting these from the observed table.
Just to be clear,
Yes.
all of this that we're doing right now is the chi-square key.
Is to get the chi-squared value,
Okay.
which still we then will use to find the p-value. But finding the p-value will be like what we did yesterday.
Right.
Once we have chi-squared, we'll do a chi-squared CDF like we did yesterday. Okay?
Yeah.
That's where we still gotta go with this. If you don't wanna do this, then you have to do all those 9 numbers by hand,
I'd rather do this than the pizza.
okay?
Yeah.
Just saying. Both have their, you still have to do all the expected counts by hand. You already had to do 9 calculations by hand.
Yes.
So, just saying. Alright, so there's that. Now what we're gonna do is we're gonna hit second mode, to go back to the main screen for a moment.
Where's the quit button?
Right here above mode.
Oh,
Second mode.
okay.
So quit because it's in blue. Alright, you're gonna hit, now we're gonna go back in the matrix menu. Second, the X to the -1 button, which is the matrix menu. And we're gonna go over to edit again. Now we're gonna go down to matrix B. And we are going to enter the expected counts.
So it's 3 by 3?
It'll be a 3 by 3 again. They'll be the same thing. The observed and the expected should have the same dimensions. Okay? If they don't, this calculator's not gonna do this right. So it's a 3 by 3, and then we enter those expected counts from the expected table. The first one is 34.22. Is everybody okay seeing where I'm pulling these numbers from?
Yeah.
Yes.
The expected table. The next one is 30.56. Then 34.22. Be really careful, kind of, don't go don't go too fast with this, guys, because the calculator sometimes will make a mistake and you won't realize it makes a mistake. Always at the end, go back and double check and make sure you entered them all correctly. 10.72, 9.57. See, I made a mistake. Okay. Double check, make sure everything's typed in correctly because you don't want to mess this up. Once you're sure everything is in correctly, you're going to hit second quit again. All right. So, now what you're going to do is you're going to hit you're going to go to stat, Once we've got our matrices in there, we're gonna go to stat. We're gonna go over to test.
So we hit quit again,
Mhm.
and then go back to matrix?
Yeah, hit second mode to quit, go back to the main screen, and then go to stat. And scroll over to test. Okay? We're gonna scroll down, 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 to down, to down. I don't know which one it is. Keep going down. It's on down. Right there. Chi-squared test, right there.
The little funky looking X.
Yeah, it looks like it's a funky X, which that's
Okay.
what chi-squared is basically. So it's a funky looking X right here, chi-squared test. By the way, there's a goodness of fit test right there too, but guess what? It's almost better to just do it by hand. There's all these tests actually that I've had to do all by hand all this time. And there are ways to do it on the calculator, but it takes almost more time to do it on the calculator than to do some of these by hand, honestly. This is the exception, the one we're doing right now. We're gonna go to chi-squared test, which is letter C. It's automatically gonna have the observed as A and the expected as B, but if for some reason you wanted to use C and D or reverse it or whatever, you could go and change it. But I would suggest that you put the observed in as A and the expected in as B and just leave it. You're gonna go down to calculate. And we're gonna hit enter. Boom. Oh, it even gives us the p-value. We don't even have to do the chi-squared CDF.
I wish I wrote all this down.
So that's the p-value right there.
Yeah, and it gave us the degrees of freedom too. We haven't even talked about how to find the degrees of freedom yet.
Okay.
For this kind of test. So this test will give you the chi-squared value, it'll give you the p-value, and the degrees of freedom, honestly. You've got all that right here. We just have to put a matrix in the matrix menu. You probably did, when you did matrices in Algebra 2, you did not put matrices in the calculator that way. There's always an easier way, like to put just a general matrix in the calculator. If you hit, so like we've got this right here. Did somebody write this down? Write these down, these numbers down. Real quick, somebody. So we have them.
Oh, I wrote them down.
Okay, good, because I just want, and everyone else can write them down too, but just to, we want to have them to compare to what we get on the notes here in just a minute.
Wait, is that different? Is it a different
Okay.
test? Oh,
No, that's it. That was it.
mine was different, I think.
A lot different?
No, it was 0, 0, 1, 2, 3, 3, 2, 4, 4, 8.
Hold on a minute, that's all. Stat, test.
0, 0, 1. Then I got 2, 3. Like it says, yeah, mine are different. Hold on.
I don't think that'll make a big difference, but you always want to make sure you put the correct numbers in the tables
Mhm.
or in your matrices.
I thought I did.
Is the chi-squared value the same?
No, it's 18. I got 18.00153.691.
You may have typed the value wrong in the table, but it must have not been that much wrong to throw it off. Because
Okay.
regardless, your p-value is still that p-value is still pretty
I'm
low.
gonna look really quick.
And it's gonna probably not affect, it's not, I mean, the P's
Okay.
value is gonna be low
30,
here.
39, 31. Oh, I put 31. That's why I put 31 instead of 30.
Okay,
11, 1, 19, 43, 35, 35.
okay,
That's why.
alright.
So let me write those down. T, 7, 9, 3, 1, 5, 1, 0, 0, 2, 8, 2. Okay.
Alright, we good?
Yep.
Alright. Just FYI, this is not to do with this, but just FYI, you probably put matrices in this way if you hit alpha zoom. We can't do that with observed and expected though for this test. We have to put them in the matrices menu. But if you want to do something algebra with matrices, just FYI, if you have to take a course where you have to do some algebra or whatever, I don't know, you may be done with math after this. There it is. All right, that's just my little side note for the day. All right, back to our notes. So on the notes. So they got a chi-squared value of 18.28. How did that compare to ours?
We did it.
Pretty close, right? All right, so then the p-value. So we started with, earlier we started the significance test with the null hypothesis that there's no difference in the true distributions of entrees ordered at this restaurant when no music, French accordion music or Italian music is played. And the alternative is that there is a difference in the true distributions of entrees ordered at this restaurant when no music, French accordion music or Italian string music is played. We already checked the conditions are met. Our calculated test statistic is 18.28. That's our chi-squared value we got. Okay. To find our p-value, we can use a table or use the chi-squared CDF command. Of course, if we run the whole test, the thing did it for us. The calculator just ran the chi-squared with that CDF without us having to do it. It's pretty nice. Here's how you find the degrees of freedom though. The degrees of freedom, because our table has 3 rows and 3 columns, the degrees of freedom is always the number of rows minus 1 times the number of columns minus 1. So if we have 3 rows and 3 columns, our degrees of freedom is 2 times 2, which is 4. Number of rows minus 1 times the number of columns minus 1. That's how you find the degrees of freedom for a two-way table. The reason I say that is because you could have a multiple choice question asking what the degrees of freedom is. I don't even flipping care about the whole test. I just want the degrees of freedom. It is not in your time. It'll be time consuming for you to run the whole test when you don't even need that. Okay? You don't even need to check conditions or do anything. All you need to do is to do row total minus 1 and column total minus 1 and multiply those two numbers together. So if I had a 4 row, 5 column, my degrees of freedom would be 3 by 4. 3 times 4, 12. If I had a 7 row and 9 column.
48.
Yep, 6 times 8, 48. Okay? I do recommend, mental math on the fly when you're in the heat of the moment on a test or whatever. You're more likely to make a mistake. I welcome you to use your tools appropriate strategically, not to make a little simple math error.
That's going to be how to get the degrees of freedom from a table.
No, just at all.
At all.
How to get the degrees of freedom. We're not going to, from a two-way table. Yes, I'm sorry, I misunderstood what you were saying. Yes, from a two-way table, that's how you get the degrees of freedom. Row total minus 1 times column total minus 1. And so then to find the p-value, they did this. They looked at between these two numbers, and it fell between those numbers. For chi-squared here, the corresponding p-value was between 0.0025 and 0.01. Doing it on the calculator, they got 0.0011. How does that compare with ours? The answer that we had, Logan, are you listening?
Yeah.
How did that, so this is what they got on the calculator, 0.0011. How did that compare with our p-value we had earlier?
That's about it.
That's about it, isn't it?
Yeah.
Pretty close. That's definitely, we never did specify an alpha value here, but what do we use when we don't have a specified alpha value? What's the default alpha significance level value?
Yellow. Forget this one. The funky looking symbol.
It's the little alpha, looks like a fish.
Oh, I just.
What's our default alpha value?
Was it?
Yes, 0.05, yes. 0.05, 5%, that's our default when we don't have a specified one. 0.001 though, that'd be less than 0.01 even if we had alpha equals 0.01, that's less than that. So if the P's low,
The null must go.
The null must go. We reject the null, and we can say there is convincing evidence for the alternative. So interpreting our p-value, assuming there's no difference in the true distributions of entrees when no music, or when all three of those treatments, those different kinds of music, there would be that percent chance, that's supposed to be a period right there, not a comma, 0.0011%, that'd be the probability of observing a difference in the distributions among the three treatments. So what conclusion would we draw? Because the p-value is less than our default alpha equals 0.05 significance level, we reject the null. We have convincing evidence of a difference in the distributions of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. Furthermore, the random assignment allows us to say that the difference is caused by the music that's played.
But I thought it fit in between the thing.
What do you mean?
Go back one. Yeah, it falls in between.
It falls in
0,
between
0, 2, 5.
these two values right here, which are both less than 0.05.
Right.
In fact, they're even less than 0.0.
So even if it falls in between that, it's still going to be.
But that's less than 0.05, right?
Yes.
That's what matters.
Okay.
It's even less than 0.01, even if our significance level is 0.01.
Yeah.
But by default, we do 0.05 as our significance level. All right, questions on that? Chi-squared tests.
I get this right now, but just to be safe, will you help me on the test?
On the test?
Yeah.
Well, we're gonna review. I will definitely help you before the review.
All right.
On the test, it's the test, but I'll help you plenty on the review. We'll do some more problems this week too, of this. All right, so suppose the condition, and I'll help you today when we start looking at problems. Suppose the conditions are met. You can use a chi-squared test for homogeneity to test this. If there's no difference in the distribution of categorical variable for several populations or treatments, that's what we just got done. We just did a chi-squared test for homogeneity. There is a difference in the distribution of a categorical variable for several populations or treatments. Start by finding the expected count, assuming that the null is true. We always check the conditions first. All those expected counts need to be greater than 5. We did not really say that, but if you go back and look at your expected counts, the lowest one we had was 9.57. That's bigger than 5 though. Once we have all the conditions checked, we've stated our hypotheses, and we calculate our chi-squared statistic, observed minus expected, quantity squared over expected. Again, we'll use the calculator to do that for us. We do have to find the expected counts though. That we'll have to do by hand. Okay? Once you do all that, where the sum is over all the cells, including not totals in the two-way table, if the null is true, the chi-squared statistic has approximately a chi-squared distribution with degrees of freedom equal to the number of rows minus 1 times the number of columns minus 1. And the p-value is the area to the right of chi-squared under that corresponding chi-squared density curve. Of course, if you run the test on the calculator, it's going to find all that for you, do all that for you. Okay? But again, on a multiple choice question, you may just be asked to find the degrees of freedom, perhaps. That might be part of the answers. You don't want to have to do that whole test if you don't have to. So knowing how to do it by hand is a little bit helpful too. Follow-up analysis. The chi-square test for homogeneity allows us to compare the distribution of a categorical variable for any number of populations or treatments. If the test allows us to reject the null and of no difference, then we want to do a follow-up analysis that examines the differences in detail. Start by examining which cells in the two-way table show large deviations between the observed and expected. Then look at the individual components to see which terms contribute most to the chi-squared statistic. The ones that had the largest deviations were these two right here. You did do that. Okay, here is the differences. What they've done right here is figured out the deviations here for each one of these. So those had the two biggest differences right here. Looking at the output, we see that just 2 of the 9 components make up the chi-squared statistic, contribute about 14, which is almost 77% of that total. These are you look at your individual chi-squared values for each one of those. That's where you would have to do it kind of by hand if you did that. So we're led to the specific conclusion that the orders of Italian entrees are strongly affected by Italian and French music. All right, now we're going to kind of switch gears a little bit. Another common situation that we have here that leads to a two-way table is when a single random variable, let's see where we're at, actually. Make a decision here. We're gonna change things a little bit, change the plan a little bit here. So what I'm gonna do is we're gonna stop here. We're gonna do just problems on this chi-squared test for homogeneity before we do the chi-squared test for independence, okay? Because this section's a little long. If you haven't looked, it's almost 30 slides long. So we're already on 19 right now. So we're gonna stop here. I'm gonna give you some problems over just this for a little bit to give you some time to practice with just this one a little bit. On Monday, change of plans, the review, I will hold off on giving you the review now until Tuesday, because on Monday I will have a video, over, an Ed Puzzle video for you to watch over the rest of this lesson. I'll make a video lesson for everybody of this one, and then we'll do the review on Tuesday in class, okay?